Okay, civil engineering students, I wanted to share with you how we're going to size what we call a spread footing. And this is in lesson 3.2.9, sizing a spread footing. If you look at the PowerPoint on this one, very good PowerPoint and as far as illustrations. Most of your commercial buildings are going to come down with a column. The load's going to come down the column and it's going to have to rest on a footpad. And this is called a spread footing. And the goal here is to make this pad big enough so that it will hold the weight that's coming down on it, and also considering what the ground underneath it is like. So if you look at all the loads from the roof, the second floor, the first floor, all those loads funnel down into the footpad, and then the soil pushes back. Remember your free body diagrams, the soil pushes back. So we got to make sure that this force pushing down with the area given is not greater than the pressure pushing back. Otherwise, you'll have the leaning tower of Pisa and things will sink into the ground, right? So I'm going to do this first little problem for you here. It's a long word problem, but really there's not a lot in there. It just says the column will carry a load of 32 kips. That's a shortcut for saying 32,000 pounds. It rests on a spread footing that's 4x6 and it's 1.5 foot thick. Okay. So it says if the footing rests on silty sand, can the footing safely carry the load? Now, the type of soil, if you look back in your PowerPoint here, they do have a table showing you what kind of soil you might have. Like sand has a bearing pressure of 2,000 pounds per square foot. Silt has 1,500 pounds per square foot, sand with fine. So I would say in our case, silty sand is probably going to be 2,000 PSF, right? So you look at this table to get the allowed soil bearing pressure, okay? So let's see if we can work this out here as far as knowing the load coming into the column, knowing the size of the footing, and knowing how thick it is, and knowing that we rest on silty sand, which is 2,000 PSF capacity. So I'm going to pull up my little ladybug camera here. And first of all, it's helpful in these to draw a picture. So I draw a picture of the 6x4 foot pad, the column coming down with 32,000 pounds coming down on it. We're setting on silty sand, and we know that the pad is 1.5 feet thick. So we've already established from the table in your PowerPoint that the silty sand will allow a Q allowable, or soil bearing pressure allowable, is 2,000 pounds per square foot. Now, the way we do these is sort of a backdoor approach. We actually calculate, we take the thickness out of the equation, and that leaves us only area we have to worry about. Like the area, the size of the footpad in area is really what we want to come up with. So we go ahead and take the thickness out of the equation in terms that concrete weighs something. So when you got 1.5 feet of concrete, it actually weighs 150 pounds per cubic foot. So if you take the thickness of the footing times 150, you'll get a how much the bearing pressure you have to account for just due to the weight of the concrete itself. So if you take the 1.5 thickness times 150, you'll get 225 pounds per square foot, which means the footpad itself is using that much of the soil bearing pressure to hold its own weight up, not the weight of the building. So we have to get a Q net, which is the soil bearing pressure minus the bearing pressure due to the weight of the footing. And that says our limit here that we're allowed to have coming into this footpad is 1,775 pounds per square foot. So that's what we're looking not to exceed with this footpad. And I think this question was worded, are the existing footpads good enough to support this new building? So if you look on down here, we're looking at if we go ahead and calculate the area required to support 3,200 pounds, we divide that by the allowable soil bearing pressure that still remains. We still have 1,775 pounds per square foot remaining. If you take the load in the column divided by the area per square foot, the pound per square foot allowed, you come up that the area needs to be at least 18 square feet. So in other words, this width times height here, this width times length has to be 18 square feet. Well, it turns out ours is 6 by 4, right? So it turns out that we have a 24 square foot area. So that's good because it's larger than the 18. Again, sort of a backdoor approach, takes a little getting used to. Now, there is another way to do this, to look at it, that I think helps students understand it a little better. Another way we could solve this is we could actually add the weight of the pad. So if you take 150 times the volume of the pad, just take the whole volume of the pad, 150, the density times 6 times 4 times 1.5, this whole big foot pad weighs 5,400 pounds. You add that 5,400 pounds to the load from the building coming down, and you've got a load of 37,400 pounds going into the ground, right? Counting the foot pad. Well, then you just calculate the stress it's putting on the ground, which would be that big load, including the weight of the concrete, divided by the area of your foot pad, which is 6 by 4. And so you get a stress on the ground of 1,558 pounds per square foot. Okay. And then since 1,558 is less than the 2,000 that silty sand will support, you know you're okay that way too. So that's just another way of looking at it. Again, the spread footing calculations are a little bit backdoor, but it really makes sense that way. If you go ahead and take the thickness out of the equation first, then you're only looking at the area of your foot pad that you need to come up with to have a successful and safe building.